MSSM search, and we can put a limit on the charge Higgs, for example, of the order 80 to 90 GeV, and the limit on the CP even and CP odd of the order of 100 GeV, just from this experimental search for chargino and neutrino.
In this case, how can we differentiate if they are coming from supersymmetric chargino and neutrino, or coming from Inert Higgs doublet model?
Well, those are scalar, those are fermions. While I think
yeah, but final
the final state will be the same. Yeah, of course.
Final state will be the same.
Yeah,
so
final state is just you can, for example, in here you can get trileptons plus vicinity, and you can get also the leptons from in this process, for example.
In the two models, MSSM and Inert doublet Higgs models, final state will be the same. So
it's not, well, there's some studies, but it's not exactly just using the data, not but the cross-section, you have to compute the cross-section in this model, the cross-section here and the cross-section here, because they're different cross-section. They are not the same, but you can just use the shape of the data. I'm not saying that it's exactly just from the data, you compare your data with when you let the final state decay in, and of course you put the cuts and everything. And then you compare to the data, but based on your cross-section, not on the MSSM cross-section. And the kinematics of the cross-section, there is a big difference between fermion final state and scalar final state. So okay, so now I move to Higgs to gamma gamma. This I already discussed right here in the Joburg Club. So Higgs to gamma gamma, as you know, so it's how much time I have? 1 hour. Okay. Well, the dominant contribution for Higgs to gamma gamma is coming from W loops. The top contribution is very small, and it interferes destructively with the W. And so in this model, you can have this charged Higgs loop, which can contribute to gamma gamma. So if they are constructive with the W, we can have some enhancement. If they are destructive with the W, so then you can have the suppression. And so for Higgs to gamma gamma, so the amplitude is given just by this quantity here. So means that if this coupling is of the same sign of the contribution with the W, they can enhance the gamma gamma. And if it's negative compared to W, so then there will be some destructive interference. And so it happens that in the inert Higgs doublet model, so the charged Higgs contribution in the gamma gamma and in the gamma Z, they come with the same sign, because this is just the coupling of the Z to a pair of charged Higgs. So it's exactly the same sign that contributes. So that means that those two channels, they will be correlated in this model. And so here they just show you how the phenomenology in this model looks. So if the dark Higgs is 75 GeV, which means that the invisible decay is closed, everything looks like standard model. dU bar at 60%, WW of the order of 20%, tau tau of the order of 7%, and ZZ, CC, and gamma gamma. Here you can see for the gamma gamma there is some small enhancement. I will explain this. So this is just the charged Higgs contribution. And so if the invisible decay is open, if NK equal to 60, so that the Higgs can decay invisibly, you can see that once the invisible decay is open, it dominates. But you can see here there is some region when this coupling, the coupling of the Higgs to the dark matter particles become equal to 0, because this is proportional to MK minus mu2 squared. So then you can have, again, the standard model picture. So dU bar, WW, tau tau, and so on. So, but we have already some limit on the invisible decay. This is what I will discuss just in a few minutes. This is just to explain the gamma gamma excess, but as I said, I no longer believe in this gamma gamma excess. So you can have this gamma gamma enhancement for if the charged Higgs is less than 180. It depends how much you want to enhance this gamma gamma, but if the charged Higgs go up to 500 GeV, you can still have some 3 to 6% enhancement in the gamma gamma. And as you can see here, so gamma gamma, gamma Z gamma is all the time smaller than gamma gamma. This is mainly due to this factor here, which is compared to this, to the gamma-gamma factor, which is 1. Here is 1 minus this quantity is the suppression factor, this one. So that's why you can see the ZZ is all the time small. So here you can see the enhancement is only happening for lambda 3 negative. Lambda 3 is exactly the coupling between the, lambda 3 is this quantity. So if it's negative, it's constructive with the W. If it's positive, it's destructive with the W. And this is exactly what you can see here. For negative lambda 3, it is constructive, so we have the enhancement. If it is positive, so it is destructive. So this is just the correlation I was talking about, since gamma-gamma and gamma-Z, they have almost the same origin. This is just the charged Higgs loop, but the gamma-Z is all the time a bit smaller than the gamma-gamma because of the Z charged Higgs pair coupling. Okay, now I move to the invisible decay of the Higgs in this model. This is just to remind you, this is what I said. So the experimental limit on the invisible decay is around 60%, but from the global fit analysis, so this limit is of the order 20 to 30%, it depends on the model. And so in this model here, so the Higgs can decay invisibly to chi-chi, with chi either the scalar or the pseudoscalar. So it just compute the branch ratio, which is thus Higgs going to chi-chi divided by the total width. The total width is just the standard model plus the invisible part. And this we know very well because in the Inert, the coupling of the Higgs to standard model fermion is exactly like in the standard model. So that means that the standard model decay rate is just 4 MeV, as we know. This you just can take from some Higgs, I mean the handbooks written by for the LHC, or you can calculate it. It's very easy to calculate this one. And the invisible decay, the partial width of Higgs going invisibly, just the couplings, and this factor here divided by this quantity, and this lambda, we know it's either lambda L or lambda A. And so we calculate this, it's very easy. So then this invisible decay is only depend m chi and on this coupling here. So this is the scatter plot we have. So this is just the dark mass, and this is the coupling, absolute value. And so this is the 65% from the experimental search. And this is the global fit analysis, 30%, 20%, and 0.1%. It depends. So if you believe in the experimental search, so that means that all this area is already excluded, means that this coupling should be less than 2 10 to the minus 2. If you believe in the global fit analysis, this coupling should be of the order of 10 to the minus 2, more or less. So it's, the red band, so if you ask, we'll explain this later. So this is just the 3 sigma band of the Rayleigh density. So Rayleigh density only show up in this close to the, because you have chi-chi, it goes to the Higgs. And when you reach the resonance of the Higgs, so the Rayleigh density starts to have some enhancement. And this is only this region here is allowed. If the invisible decay is open, so the dark mass should be in this area around 53 GeV, 53 to 55 GeV mass of the. So we did the same thing for the spin-independent cross-section. This is very easy exercise also to do because you have the chi will scatter on the nucleon. It goes to chi nucleon. So there is only one diagram here. It's T channel. You have chi and nucleon, and you have the Higgs exchange in the T channel, and then you have the Higgs. So then this process is only sensitive to this coupling here, Higgs to chi squared. And so I just eliminate these couplings in terms of the invisible decay. I can relate this coupling to the invisible branch ratio. And then, so I can relate the spin-independent cross-section to the branch ratio of the invisible decay of the Higgs. It's very easy exercise, just compute this cross-section. It will depend on this coupling square, but this coupling square is exactly related to the partial width of the Higgs going invisibly. And so we have this relationship between the invisible decay, branch ratio, and the spin-independent cross-section. And so we did this scan here, this scatter plot. So here are just the invisible decay branch ratio. This is 30%, 20%, 10%. So this is 30%, 20, 10. I think this is 5%. And this is examined limit, the actual limit. And you can see, so there's 30% is already, part of it is already excluded. But there is also two limits. This is the projected lux experiment and also the xenon 1 ton projected sensitivity is up to here. That means with this projected measurement, we can already with lux you can exclude so invisible decay branch ratio up to 4%. But with this experiment, you can be sensitive to 1% branch ratio of the invisible decay of the Higgs. But we did even a likelihood analysis with TC and SMING. And those are the information we get in the likelihood. So in age, relic density, S parameters and T parameters. And also we include this branch ratio of the invisible Higgs. We just use the experimental upper limit, 65%. And also we use the CMS number for Higgs to gamma gamma. This is the likelihood how it looks, and this is the chi-square. So everything is Gaussian, except here we include this error function. And so the profile likelihood for this model look like this. So here there is some, it's excluded because when you have chi go into X and X go to W, because in this region here you have the annihilation could give a W, and W give too large cross-section for the relic density, and so this area is excluded. So then what is allowed is just this area here when the dark matter mass is less than 100 GeV, or because the dark particle could be either this one or this one, there is no preference. So even if the best fit is located here, it could be also located here, because when you run your likelihood, you should stop at some stage, and so just accidentally but it could be, the best fit could be here or here, it's the same.
I'm sorry, I thought the direct diameter search, the xenon constraint has ruled out a lot of the phase space already. Could you show the plot again?
Yeah,
I thought
you could say more than 30% is already ruled out. But well, there's something I did not say. Yeah, it's about 30% already, 60% is already excluded. But
okay.
Well, here there is a lot of uncertainty coming from this this form factor of the Higgs to nucleon, which appears here. There is still some large uncertainty there, which could affect even the 30% is limit. I mean, I could just play with this form factor and I could push it down if I wanted. Okay, so this is the profile likelihood for the inert. So this here has nothing to do with the relic density. This comes only from ST parameters constraint, because you know this T isospin violation does not allow to have a large splitting between the two Higgs. So this is mainly the T parameters. And well, when the mass are quite low, so here also there is some limit from ST parameters, but all this area is ruled out from relic density constraint. This is just the same, but in the other plane, in A and charged Higgs, and so you can see the splitting is not very large over here, but for low mass, the splitting could be of the order of 250 GeV. Here is the same, so as function of m chi and the coupling between the standard mode Higgs and the dark matter mass. Yeah, I just wanted to show, just from the likelihood analysis, we get exactly the same result. The first result I show you for the invisible decay of the Higgs, but if the range of lambda chi chi allowed is the order of 10 to the minus 2 almost, so of the order 10 to the minus 2. So when the invisible decay, of course, is open, so this coupling should be quite small. So now I move to the triple Higgs coupling. As you know, so we already know that LHC, CMS, and Atlas already measure some of those coupling, Higgs to fermion and Higgs to gauge boson, but in order to establish the Higgs mechanism as the correct one for the electroweak symmetry breaking, we need to measure the triple coupling of the Higgs and also the quartic coupling of the Higgs in order to reconstruct the scalar potential. And if the measurement of this triple coupling is precise enough, so it could give also some information on a lot of new physics models, and it could be also used to distinguish between various beyond standard models of physics. This triple coupling can be measured in, at LHC, it can be measured in this process here, for example, glue going to Higgs, and then the Higgs split to two Higgs. Or it could be measured at the linear collider in the same process. You have the Higgs trigon, but the Higgs split to two Higgs. Or you could have this WW fusion, which you get Higgs from WW scattering, you get Higgs, and then the Higgs split to two Higgs here and two neutrinos here. The same process you can have it also for the LHC, but for the LHC, for this process, the cross section is quite small. Even for this one, the cross section is very small. I will show you. This is the at the LHC, so you have the glue, you produce the Higgs, and the Higgs split to two Higgs. So you have the vertex contribution, you have the box. There's three topologies, this box, the crossed one, and the other one with this gluing coming from there. This is the cross-section at the leading order, and this is at the next leading order. So you can see it's a factor of 2 between the two contributions at the leading and the next leading. The K factor means that the K factor is roughly 2. But you can see, so the triangle are quite small, this one, but the box are quite large. You see it's 37 compared to 5 there, or at the next leading order is 70 compared to 9. And also the interference between the box and the vertices, it's destructive. So it's quite large and it's negative. So that means that the cross-section at the end is going to be quite small because of this destructive interference between the vertices and the boxes. And this is the size of the cross-section here, but this is a cross-section times the branch ratio. This is the 2 Higgs decay to B bar. The 2 Higgs, one Higgs decay to B bar and the other one goes to jet. This is BB bar and the other Higgs goes to W, that goes hadronically. And this is one Higgs go to BB bar and the other one goes to tau. This is the smallest cross-section. All those, they are large QCD background. It's just, you forget them. So most of the people, they concentrate on this one, on the Higgs. One Higgs goes to BB bar and the other one goes to tau tau. Or one Higgs goes to BB bar and the other one goes to gamma gamma. Even the cross-section is quite small. It is possible to reconstruct the triple coupling from that one. You can see, so the cross-section is after the Higgs decay, one goes to BB bar and the other one goes to tau tau. One tau decays, this is another one. One Higgs goes to WW, one Higgs goes leptonically, and the other one goes to jet. The cross-section, they are the same. This is exactly that line here. Because at this 125, they are the same cross-sections. But for this one, this channel gives the best prospect for this measuring the triple coupling of the Higgs. This one also is, the cross-section as you can see is very small, but it's very promising, so to recall, especially for high luminosity for the LHC. When I say high luminosity means the maximum 3000 inverse femtobarn, you can do this measurement with this one. This one is also quite good, but it gives a very small signal to background ratio, so the 2 Ws decay fully leptonically. There is also the other possibility that you get 4 Ws in the final state, but also it's hopeless. Here I just take the cross-section at the next leading order and I play with this lambda here. This lambda is just the ratio of the triple couplings normalized to standard model 1. I just put it like 1 plus some correction, delta, and we can see what kind of correction we need. I mean, if I plot as function of lambda, you see it's a kind of parabola because of course you have some lambda square and some lambda. So the minimum is around 1.5, I think. or somewhere here. It depends. If you look into this is the blue line is the leading order, and the red line is the next leading order. But you see, so here it's what is preferred is this correction to be negative. If the correction is negative, that means that you reduce because this is just the triangle contribution. If lambda, this correction is negative, you reduce this one, and if you reduce this one, so that means that there is a small interference between them, and then you can get some enhancement. If the delta is positive, so then you reduce the total cross-section by some amount, and you need a very large delta to get the cross-section going up.
For your corrections, the NLO
Yeah.
is twice the LO.
Yeah.
Is it possible NLO is also for the 100%?
Yeah, of course.
Could be 0 or 0.
The NLO mean?
NLO.
Ah.
NLO.
Well,
You don't know. How do you know this?
I don't know.
It could be much more.
Here, the K factor is of the order 2 in this process. Means that you remember this is what you are saying now?
How do you know if the NLO will not be?
But this I don't know. If you don't calculate, you cannot know. So this, you see, from here to here is exactly factor of 2. Same.
So it's possible that in NLO it could be.
Yeah, it could be negative in the other sense. I don't know. So nobody knows if you don't calculate them. So there's no principle.
So it's not trust.
But well, in general, so it's when you do the sensitivity to the normalization scale, you can see that the NLO behaves much better than the leading order calculation. But well, I cannot see. You have to calculate those correction and see if it's.
I remember that, if I remember correctly, the standard model pair Higgs creation is about 40 to 50 femtogram.
Yeah, it's here. It's 30, about 30 femtogram. This is almost 30 femtogram for the NLO. For the leading order, so it's you have to look for delta equals 0, the standard model. It's just this line. So for the leading order is 18, 17, 18. And the NLO is 20 something. It's almost 30.
Previous slide, you wrote about.
Yeah, I wrote them. This is 30 and this is 18. So it's,
I remember it's 40 to 50.
it depends on the scale. So it's there is the normalization scale. So there is some up to 30% uncertainty on those numbers. So 30. When I said 30 femtogram, you have to include some 30% uncertainty from a lot of from the PDF, from the normalization scale. There's a lot of parameters that enter that. So this is just I pick up. I think well, it's here. We take the invariant mass of the 2 Higgs as the factorization scale and the normalization scale. But if you change this, you can change those numbers, and also the PDF uncertainty will also change the cross sections. So okay, this is just the behavior of this cross section as function of this correction, small correction that I wrote there. Well, I show you this because we did the standard model additive correction to the triple coupling. Just by this decay, the Higgs can go to 2 Higgs. You have all those Feynman diagrams, so then you have to, it's ultraviolet infinite, so you have to do some renormalization. This means that you have to add counter terms and you have to fix your renormalization scheme. We did the on-shell renormalization scheme, so the coupling is just given by this quantity, so we need to renormalize the Higgs fields, the Higgs mass, the W mass, and the Z mass, because we use the on-shell definition for the mixing angle, SW equals this quantity, and also we normalize the electric charge. I don't go through those technical details, but this is very known scheme, the on-shell scheme, so for the standard model it's very well known. And the result we get is this one. So this is the Q squared, because they take one Higgs off shell, which decay to 2 Higgs. And this is just the correction. This is delta as function of the Q squared. This is the top bottom contribution, and this is the W and Z contribution, and this is the total contribution. So as you can see, so it's completely dominated by the top contribution. This is very well known result. So for this scale for Q squared equals this, it's known that the correction is of the order of 10%. But as you can see for high Q squared, so the correction could be also negative. So the order even could be quite large. And so to be compared here, for the standard model, I would say that we are in this negative region here, because in most of the Q squares, so the correction are quite negative. Maybe they could enhance the cross section. But this is, I mean, we cannot trust this because it depends on the Higgs split to 2 Higgs. You have to include this in the physical process, not in that one. So this we are still working on. This is work.
Which diagram is the most significant?
The significant is just the top one. This one.
Remember that Kahneman and the
Yeah, they did it both diagrammatically and from the effective potential, and the top contribution is the dominant contribution. Now, we did the same thing for the Inert Higgs doublet model, and so there you have the top contribution, but you have also the dark Higgs that contribute. So you can have Higgs here, and you can have charged Higgs here. You can have all these diagrams here. And so, since those couplings here are quite important because they are proportional to lambda from the scalar potential, so those corrections could be quite large. Those has been done by Kanimura-san for the Higgs doublet model. And the correction could be of the order of, in some case, of 300% even. So here we confirm the same results. So the correction could be quite large. So here, just the correction as function of the Q squared. And here, we just assume that all the inert Higgs are degenerate. Ma is Ms is charged Higgs. And this is 200, 300 GeV. So for 200, the correction is similar to standard model, which is dominated by the top. So 200 is of the order of the top mass, so it's exactly the same. But when you take, for example, 300 GeV, you have this threshold effect which appears here. This is 600 GeV. Off-shell Higgs of the order of 600 GeV can split to 2 charge Higgs of the order of 300. This is just the threshold effect, and the same effect you will see at 800 GeV when I go to 400 GeV here. So, but just to tell you that those corrections could be huge, even more than 100% if I, in this case, for example, this large correction comes from the threshold effect. If I take 500, which is still okay with perturbativity, unitarity, and everything, I can get more than 200% correction near the threshold region. But this shape of correction here, I would say that in most of the case, you can see the correction are positive, well dominated by positive quantity. So to be compared with the plot I showed you before, that's going to suppress the double Higgs production of the LHC. Well, as I tell you, so how much time is left? 10 minutes? Or?
Okay, 5 minutes.
Okay, the triple Higgs coupling also you can measure it at the linear collider, but at the linear collider you have so many diagrams, so you have all this, but the most important one is this one, because this one is sensitive to triple coupling, but you have those. The dominant contribution comes from this diagram, and those, they have some contribution, but it's smaller compared to that one. The cross-section at 500 GeV is rather small. It's 0.14 femtobarn. That means that if you want to measure this triple coupling at linear collider, you need to have a very high luminosity, which is 1000 inverse femtobarn. And so I did the same exercise here. So we just write the coupling, the standard bond coupling, as 1 plus some correction, and plot this cross-section. So it's the opposite to the LHC. In the LHC, you see we have some enhancement for negative correction. you can enhance the cross section. But for linear collider is the opposite. For negative lambda, you have some suppression, which is normal because this cross section is dominated by this coupling. So if delta is negative, you reduce the cross section.